Video covers the solution for question 1 in the module of Mohr's circle of 2D stress and strain transformation. So in the following question, the state of stress at a point shown on the element, determine the principal stress and the maximum in plane shear stress and average normal stress at the point. Specify the orientation of the element in each case, show the results and on each element. So we're going to use Mohr's circle to solve this. So the first thing we want to know out, what have we been given? What do we know about the element? Well, we have been given that our normal stress in the x direction is negative 30 megapascals. We've also been given a shear stress of negative 12 megapascals. So in order for us to solve Mohr's circle, we have a few steps that we'd like to follow. I'm going to write them down and we're going to solve as we go along. So Mohr's circle, you might recall something called CR squared. So they're basically the initial steps that we want to take. So the first step, step 1, refers to our C, which is finding the center point. So C, and we will find that by finding our average stress, average normal stress, which is just the x component plus the stress on y divided by 2. So as we saw before, we only have an x component of normal stress. So we'll just have negative 30 divided by 2. So our average normal stress is just negative 15 megapascals. Our step 2, it refers to the first R, which is our reference point. We usually call this reference point A. So A is just a coordinate of our normal stress in X and our shear stress, which means we've already been given these ones. So negative 30, negative 12. That's where we'll have our reference point. Then the last step before we start drawing, step 3. We want to find that last R that we refer to in there, and that's our radius. Radius, we can just simply calculate from square root of our normal stress in X minus the average normal stress squared plus the shear stress squared. And we already have all these values, we just plug them in here. So minus 30 minus 15 squared plus our negative 12 squared. We'll find that this is 19.2094 megapascals. So we have our center point, we have our coordinate for our reference point, and we have our radius. So how do we then start with our Mohr circle? I usually just start with my horizontal line, as such. I indicate my center point, which will be somewhere right here. So remember, our center point is located on the negative axis, which means our shear axis will be slightly on the right-hand side. Okay. And again, my shear. In this case, I'm going to have my positive at the shear at the downward direction, and positive normal stress towards the right. Okay. All right. And just recall our center point is the center of, the center point of the circle is obviously where my C is. Then I'm just going to mark out where my different points are located. So remember our reference point, -30, -12. So again, left-hand side is my negative normal stress, and upwards is my negative shear stress. So my reference point will be located somewhere around here. You can fill that in if you want. I'll just leave that. So my A, -30, -12. Then we also have our principal stresses. I'll use this blue. So my principal stress 2 will be located here. Principal stress 1 located here. My principal stress 1 is my maximum normal stress. And then my principal stress 2 is my minimum normal stress. So before we start drawing too much more, let's go figure out what our principal stresses, what they would look like. So just by looking at this, just recall the distance between my C and my principal stresses, regardless if it's the minimum or maximum, they're simply just separated by the radius, right? So if I go ahead and write that out, my principal stress we can quite easily find that my maximum principal stress is just the center point plus the radius, and the center point is just my average plus the radius, which again, my center point is located at -15, and then we add the radius, which is 19. I'm just going to round this up now, so I add that in here as well for you guys. There we go. The maximum principal stress of 4.21 megapascals. Minimum principal stress, again, it's just our center point, but at this time we go minus the radius. So minus 15 minus 19.21, which is -34.2 megapascals. We have all this information. Now we want to find the transformed element. So we want to look at how our original x-axis is rotated. One way of thinking of it, I'm just going to extend this a little bit. In the element, this refers to my x, right? And in this case, my angle is 0. So that's when it has not rotated yet. So what we want to find this angle between here. And this is referred to 2, because it's the second element. If we had our reference point on this side, we might want to refer from our principal stress 1, right? But recall, principal stress 2 is the one which is following the x component here. So I'll show you what it looks like in the element in just a minute. So that angle there, we can simply just find this from the geometry, right? So if we look at the height, let's use a different color so it's easy to find. We'll look at the height. So from this until it cuts the axis, this is just the same as my shear stress, which is my -12. But then we also want to find this distance here. And what we need to do, so we don't actually know this distance at the moment, but we know the center point and we know how far away our reference point A is from the shear axis. I'm going to extend this. So this one here is -30. And we know up until the center point and to the axis. That's just the same as finding the location of the center point, which is our average stress. From that, we can find our, I'll extend this completely. So 10 of these ones is simply just our shear stress divided by our normal stress in X minus our average stress. So then we'll find, if we take 2 to the -1, and now I'm just going to put in the actual values for these ones. It's my -12, -30, -15. What we will find is that my 2 theta P2 is 38.654 degrees. And if I want to draw that into my element, because in the element we just need the angle by itself, right? We just divide it by 2. 19.33 degrees. So in our Mohr circle, this angle here is 38.654 degrees. But when we look at the element, we want the 19.33. So let's go ahead and draw this element. This is my y, and this is my x. So this coordinate field refers to my reference point, and the transformed element is then simply this is my element. And then my new axis, obviously this is not drawn properly to scale, as you can see with the angles. So this is my transformed y, my transformed x. I'll go ahead and note my angle in there. then I go ahead and put in my principal stresses. So again, principal stress 2 is the one that is related to my x-axis and its transformation. So negative 34.2. Negative means it goes into the element. And then our principal stress 1, or our maximum principal stress, is positive, so it goes out from the element. There. That's all we need to do for our part A. And the element. For B, we want to find the max in plane. If we have a look here again, my maximum in plane shear stress is then located at the bottom. And what does that tell us? Well, it tells us that our max in plane shear stress is just the same as our radius. So if I write that out, max in plane equals to our radius, which is our 19.21 megapascals. And then we also need our average normal stress, which is just what we calculated earlier as well up here. And that's the same as our center point. So negative 15 megapascals. So it's the center point, if you want to call it that. So negative 15 megapascals. Look at the Mohr circle. I believe it's been in one of your lectures where they talk about the location of your center point, how it's not necessarily on 0, but it's located at the point where we have our max in plane shear stress. So that's located here, which is where your center point is located, which is located at a distance of the average normal shear stress from the shear axis. But we also need the rotation of this element. So how do we find that? Well, we go back to our reference point, and then we have a look at what is the rotation from the reference to the shear axis. So let's look at the max shear axis down here. So we're just going to draw this out in there. And again, I'm just going to look at this graphically, and what I will see is that, first of all, S2. What we'll find is that we can simply just add the 90 degrees in here to this angle that we found earlier. So our 2 theta F2 is simply just our 90 degrees plus the 38.654. Right? We will find that that is 128.654 degrees. For our element, we divide that by 2, and we will find that it's 64.329. degrees. So now we want to sketch our element B. Again, we'll have our original X and Y axis. Again, the rotation is not drawn to scale, only because I have this free set blocks rather than me trying to sketch something neat. So first of all, we had a negative average normal stress, which means it's going into the element. And it will do so from both directions. It's my, well, I realized my drawing was probably not the neatest for mine. Just so I don't confuse anyone, I'll just remove this one to a new arrow out there. So if this is my X, then this is my X dash, my Y, and my Y dash, right? And again, this angle here is my 64.329. But then we also have our max in-plane shear stress, and if we have a look, it's a positive, which means it's going in this direction. So that means that the arrowheads meet at the top right corner. So if we just tilt that back to the original YX, this is the top corner. And that concludes the solution for this video. You can find the written out notes a bit further down on the Canvas.